Welcome back for video 3 from Unit 12. We continue our discussions about descriptive statistics. The focus for this video is going to be on measures of dispersal, measures of dispersion, I should say. Basically, we're talking about how spread out is the data. Is it clustered? Is there a wide discrepancy from the lowest scores to the highest scores? So when we talk about that span of data, how spread out is the data? How dispersed is the data? We're talking about dispersion. And the two forms that we'll look at in this particular video are an easy one and a little bit more difficult one for us to calculate. We'll talk about range. That's the easy one. Standard deviation, a bit more cumbersome for us to calculate. Luckily, we're armed with Excel, or at least a good calculator. So let's get this thing rolling. We'll share some video slides. Content from section 5.3 in your textbook, range, variance, and standard deviation. It's important to point out that the standard deviation is simply the square root of the variance. So even though it looks like there are three ideas coming your way, we actually calculate variance as a means to get to standard deviation. Measures of dispersion, as previously discussed, measure the spread of the data. If the data is all clustered, there is no spread. So if we take a quiz and everybody gets 100, there's no spread on the data. Everybody got 100. The range would be 0, right? There is no high score, low score difference. Everybody got 100. But if we contrast that with the quiz, it's still pretty easy, but we got one guy who cuts class, he gets a 0. So now the data spreads out. We still have all those hundreds, but now we've got to track the lowest guy in there at a 0, so the data spreads out considerably much more than we had on the first illustrative example. All right, calculating a range, it's a piece of cake. It's simply a difference. It's how much bigger is the big guy than the little guy. So for those of you who are formula fans, the range is found by taking the highest data point and subtracting the lowest data point. Here's an example for us. We're back to first year's 8 o'clock class, and we've got to find out the highest score and the lowest score. And you can just eyeball it if it's a relatively small set like this. If it was a gigantically cumbersome data set, Excel finds easy ways for us to get our hands on biggest and smallest by being able to sort the data effectively. Looks like 14 might be tiniest, and it looks like 99 is the biggest. So if we find the range on this particular class's score, it is in fact the difference of 99 and 14, and the range for this data set would be 85. So all that tells us is there's a pretty good difference between the largest and smallest. The data spreads out pretty much, right? 85 points difference. Problems with using range. It's easy to find. It's really easy to find, but it really only provides insights about two extremes on our data set. We don't know much about anything else. Like, are most of the data points closer to one of those numbers than another? We don't know. We don't know if the data clusters anywhere. So I've never kind of believed that even though range is easy to get your hands on, it doesn't describe the set of the data very well. It gives information about high to low, all right, but it doesn't really tell you, are the data points clustered anywhere? Is there a bunching of them near the high or near the low? We gain no knowledge of that. So to get more information about the data set, we resort to variance, and then the square root of that, as previously mentioned, will be standard deviation. Good news is it gives us more information about point by point. Bad news is it's much more cumbersome to calculate. Right? So variance measures spread. So on the picture in front of you on the screen, you see that the data seems to be spread out pretty far. There's a decent number to the left of that mean, and there's a decent number to the right of the mean. So if we were to look at the variance of this distribution, it's bigger than the variance of this distribution. The data is not spread out as much. It's more clustered. All right. So it gives us, again, more knowledge about the general tone or tenor of the data as it relates to the whole data set, not just the highest and lowest. To calculate variance, what we tend to do is find out how far each data point is from the mean. Okay, well, that seems to mean that we'd have to find the mean. We already know how to do that. Excel's there for us if we need it. Then what we're going to do is find out how much each data point deviates from the mean. So that's simply a subtraction problem. We're going to do a little subtractions calculators if we want. So again, I'm throwing me some deviations down there as saying I'll take each individual data point, we're referencing that as x sub 1, and we're subtracting from that the mean, which you've met previously and denoted as x bar. Okay? It's important for me to tell you some of those deviations are going to be positive. Some of those deviations are going to be negative. In some cases, your data points are bigger than the mean, and in others, they're less than the mean. So in the truest form, what we might think about doing is just finding these deviations and finding the average of them. Well, we're going to run into a problem because when we add up all those deviations, unfortunately, we get a 0. So if we sum the deviations, we will always get 0. So we get creative in our old age. And here's what we'll do. We'll square all of those things and we'll get rid of the negatives that way. And then we'll take the square root. So in effect, it's no net change. That's pretty sly. That's basically the premise. So now that we have our deviations, the next step in calculation would be to square each of the deviations. And that's our next attack. And then we'll add those. And you're like, yes. And then we'll do some square rooting. Yeah, we are. All right. So here's the process for you and I to deal with variance and standard deviation. Find the mean, subtract the mean. So basically find the deviation for each data point, square those deviations, sum those squared deviations. Now, the important thing for us to think about here, we're going to be dividing by n minus 1, where n is the number of data points. And in this context, if you look at statistics, well, we're finding the sample standard deviation. I'm going to presume for our purposes that we won't have access to knowledge about a whole population. If it were a population variance, you would divide by n, not n minus 1. But we'll stick with n minus 1. Your author's consistent with that, so that's what we'll do. That calculates the variance, which is going to be denoted as s squared. Again, since it's a sample, if it were a population, that would be called sigma squared with the Greek letter sigma. And we'll find standard deviation by taking the square root. So I want to do one by hand. So you see the process. My pledge to you is I'm never going to ask you to do this with a cumbersomely large data set. All right, if you have to do it with a cumbersomely large data set, welcome to Excel. So there's us. We're finding variance, and then variance is just square root. All right, so let's go into a problem and walk our way through. As promised, it's a small data set. We have 5 people. We got a 3, an 8, a 9, a 3, and a 5. And we've been asked to calculate the standard deviation by hand for that sample. So what do? Well, we're going to find the mean first. So that means we're going to have to add up the 3 and the 8 and the 9 and the 3 and the 5. And we'll be dividing by 5 because there are 5 data points. All right. Unfortunately, I didn't get a good look at me. It's not horrible. It's 5.6. So your next step to populate that table is to find the difference between each data point value and the mean. So we'll be doing 3 minus 5.6. You guessed it, that's negative 2.6. And the same action for the 8 and the 9 and the 3 and the 5. So each data point minus the mean calculates the deviations from the mean for each data point. How far from the mean are they? All right. And then we'll take those entries, the negative 2.6, the 2.4, the 3.4, and so on, and we'll square the deviations. So we're at 6.76, we're at 5.76, we're at 11.56, 6.76, and lastly 0.36. All right, continuing our attack to find the variance in standard deviation, we now sum those deviation squares. So if we add that column, we're going to get 31.2. On the next slide, we're going to continue our calculations. So it's time to find standard deviation. You'll notice that I'm bringing the square root in right away. So whatever we've got there inside that set, which is the sum of the deviations, that numerator player will be our 31.2. And if you remember, tracks how many data points we had. For this example, it was 5. So on the bottom, we'll be dividing by 4. All right, so as we calculate our value for standard deviation, it would be the square root of 31.2 over 4. Calculator time by del, it's the square root of 7.8. 7.8 is the variance. The square root of the variance is the standard deviation. So standard deviation is 2.79. The higher the standard deviation, the more the data spreads out. This data had a pretty decent amount of spread. We went as low as 3 and as high as 9. All right, so if we had a data stack that was much more clustered, like a whole bunch of 9, 8, 9, 9, 9, 9, then we would have had a much smaller standard deviation. There would have been less spread. The data had less dispersion. That, my friends, wraps video 3 for Unit 12. I'll be back in a bit for Unit 12 video 4, which wraps our discussion on Unit 12. See you soon.